of universe at that time. Accordingly, he proceeded. So now, Einstein's field equation, in searching the field equation of gravitation, we are guided by the fact that Newtonian theory is an approximation. Whatever result you have obtained special relativity, for low velocity you will find Newtonian result. Newtonian theory is not wrong, but it requires modification. For low velocity, you can apply Newton theory, but high velocity is fail. Actually, what was the contribution of Newton? He brought the science on the earth, and Einstein brought the science in space. Whenever you find the time, chance to go IUCAA, Inter-University Center for Astronomy and Astrophysics, then you will find that Newton is sitting under the banyan tree, looking downward direction, and Einstein is looking upward. It means he has dealt the science for space, and Newton had dealt the science for earth. Okay. Now, how field equation was found, I will not take more time because I have been given around 30 minutes, and I have to speak all this. Poisson equation, in Newton theory, the field equation is governed by Poisson equation, del to V. V is gravitational potential, rho is matter, G is gravitational constant, matter density. That is why you know. The gravitational potential actually it was proved that for low velocity, weak field, slow motion, and static body, this gravitational potential V is equivalent to magnetic tensor. With the help of this magnetic tensor Gij, Einstein studied the inverse, which is ds square equal to Gij dxi dxa. The students of mathematics and physics, they might be familiar with this result. And now, since I want to prove it in tensor form, then we have to see the gravitational V is equivalent to Gij, then you have to see that tensor in which second order derivative of Gij occurred. Riemann curvature tensor or the tensor which is obtained from Riemann curvature tensor, that is Ricci tensor Rij, which is our second order, second rank tensor, and the rho, there is actually rho is the matter density. So we have to see that tensor in which this matter density occurs, the Minergy momentum tensor, rho plus P Bij minus P Gij. Actually here it occurs. That's why the Einstein field equation becomes in this form. And since conservation of energy says that Tij is covariant derivative denses, Einstein tensor is that tensor which converts divergence denses. That's why these two are equivalent. In this way Einstein obtained this field equation. Now how he applied for the study of inverse? Again, just give up. Now, Newton equation. Equation of motion in Newton theory is given by dqxi by dt square minus del v upon del xi, I is equal to 1 to 2, 1 is 3 dimension. In theory of relativity, space and time both are interconnected, being different phenomena. You can measure the distance by scale, but you cannot measure the time by scale. You can measure the time by clock, but you cannot measure the distance by clock. Okay? But they are, he brought space and time interconnected. Einstein. And actually Newton says that both are different, those are same phenomena, but he could not actually interconnect. He could not get success to interconnect. Einstein succeeded in this one, and in Einstein's theory of relativity, equation of motion is given by geodesic equation. This is d2xi by ds square plus gamma ij dx by dx dx by dx. This is the main difference between Einstein and it. Now how relativity was applied for the study of inverse, that is cosmology. Cosmos plus logy. Cosmos is inverse, logy means Biyani. Science, you may say. Here actually in cosmology what we do? We construct the model of this inverse and try to see to what extent this model resembles the actual inverse. We apply Einstein field equation. Now at the time of Einstein, what was the position of inverse? Inverse was supposed to be static, isotropic and homogeneous at that time. Okay? Now that was called static cosmological model, which is independent of time. Now, what are the positions of astronomical observation? Astronomical observation evidences quantitative homogeneity and isotropy of matter distribution in the large. Matter, of course, consisting of galaxies. You can say galaxies are considered on large scale as point particle. What was actually, if you want to know about the universe, as per astronomical, actually theory of relativity depends on astronomy. Whatever astronomical observation indicates, that is proved by Einstein field equation. But and actually in universe there are 10 to the power 11 galaxies. One galaxy contains 10 to the power 11 stars. Our universe is the part of one galaxy, that is called Milky Way. 9 planets are moving around the sun. Okay, and I think you are familiar with this one. And now you can say how star planets are kept intact. That is, they do not fall, because they are kept intact due to their own force of attraction. Gravity, the property of gravity is to attract inwards and centrifugal force outward. In the body and the planet and star, when these two forces are equal, they are kept balanced. Otherwise, they will actually collapse. This is the main topic. Why the stars and planets do not fall on each other? They are kept intact due to their own force of attraction. Gravity is equivalent to centrifugal force. Centrifugal force, outward force, gravity, inward force. That's why they are kept intact. Okay. Now, isotropy. Iso means same, tropy means direction. By iso means it looks the same. The universe looks the same in direction. That's why he assumed that universe is of spherical type. And homogeneity means pressure and density, equal distribution of matter. Pressure and density are constant. And matter, of course, and galaxies were considered as point particles. They are behaving like perfect fluid. The expression for perfect fluid, energy, momentum, tension is rho plus. Rho is matter density, P is isotropic pressure, Vi dxi by ds. That is the motion, or velocity indicates velocity, and Gi is magnetic tension. Okay. Now he took spherical symmetric matrix in this part, and this, that is why static universe. Static means time independent. When the universe depends on time, then this is called non-static. Non-static. So Einstein field equation for the given matter, if you calculate, you have to calculate Ricci tensor and this one is multimeter tensor, etc. Then you will find and apply Ti is equal to this. T11, T22, T33, V1, V2, V3 is 0 for static universe. T4 is given by Ds square equal to Biyani dxi ds. Okay. This one, for the universe containing perfect Einstein field equation lead to this equation. Now three cases arise how Einstein universe was obtained. Rho plus P nu dash is equal to 0. Then three cases arise, nu dash 0, rho plus P 0, and both are 0. If you know x into y is 0, then x is either x0 or y0 or both are 0. Then you can have the same grammar I will use here, and Einstein equation was obtained. This one I will not go into detail how the mathematical calculations, because it is required mathematical calculation to find out this one Einstein. But this universe, that is empty, because rho plus P is 0. Rho density, P is isotropic pressure, and the flat inverse where the idea is constant, that is called flat inverse. This is called like this. This line element is also converted by inductive transformation into expanding inverse, non-static. Although this inverse is static line element, but using this transformation you can get this inverse into this one. K is constant, and it is used for experimental inverse. Next. Redshift, when light is coming from a star, then actually light is shifted towards red color of the spectrum. What is the importance of this one? That the universe is expanding, not static. Static means fixed. Now, how Einstein realized that lambda is cosmological constant, and he realized that initial stage, when there actually the non-static model was constructed by our other scientists, then it was realized, Einstein realized that there was a blunder mistake by me by adding lambda, that is constant. But later on, so many scientists came further this Gaussian coordinate system, and obtain a metric. He actually there Friedman said that the universe is not static but it is expanding, that is time dependent, and he proved it one by one. Now, how Robertson-Walker metric was defined? First, global time coordinate, Gaussian coordinate he used. Universe is isotropic, look the same in all direction, and the three-dimensional space belonging to different constant values of t are equivalent. Okay, that is homogeneity postulates. And using these three concepts, Robertson-Walker matrix to this part like this. And if you by general transformation, it was proved. This one, for k is equal to 0, it represents back space. This means T is a constant. For k is equal to -1, it represents open inverse. Or k is equal to 1, closed inverse. Okay. Now Friedman, Robertson-Walker. Actually, Friedman was a Russian scientist. He used Robertson-Walker metric. That's why it was called Friedman-Robertson-Walker metric. And he obtained the inverse for dust field inverse. Dust, that is pressure is 0. Hard dust, that is pressure is 0. And Robertson-Walker model was obtained only taking three spatial values of energy, momentum, tensor. Spatial T11, T22, T50. These two are equated, and he obtained the model Robertson. But Friedman discussed the model using pressure less dust, that is P is equal to 0, and he actually proved that there is no need of cosmological constant lambda into Einstein field equation. You have seen that Einstein field equation is given by Rij minus half Rgij plus lambda Gij is equal to -8 by Gij. Okay? He proved that for non-static, actually Einstein obtained the inverse for static model. He actually assumed that what was the condition of inverse at that time. He accordingly added lambda, the cosmological constant, to his field equation, but later on actually failed for expanding inverse. So actually Friedman actually obtained just field inverse, in which there was no need to add lambda into Einstein field equation. But later on, Eddington, astronomer and cosmologist, Lemaitre, cosmologist, actually observed that if Einstein has added lambda into his field equation, there may be some important. Why he added? And Jendovich, Russian physicist, came forward and he actually revived the issue of cosmological constant, that it is related with quantum fluctuations, and it represents, this lambda represents vacuum energy density, that is also called cosmological constant and vacuum energy density. And nowadays, actually in 2000, before 1998, it was supposed the universe is expanding, but two groups led by Rees et al. And Parmister et al. They proved that universe is not expanding but it is also accelerating, and they were actually awarded Nobel Prize in 2011 for showing that universe is accelerating also. This was due to the importance of this lambda that was called cosmological constant, and later on it was told that it represents vacuum energy density. Okay, in this way general relativity, how general relativity was used to find the study of the universe by Einstein, and in this third lecture I had to explain in a very simple way so that you could follow. Okay, thank you. If any question you want to ask, please.
Thank you very much, sir. Now, I would like to invite our second speaker, Professor Alok Pandya, sir. Sir has done his PhD from University of Rajasthan, and presently he is working in Department of Physics in JECRC University. So please have a big round of applause for Professor Alok Pandya sir.
Good afternoon, everyone. So, too many equations in Professor Rajbali's presentation. I hope you could bear it well. And in case you have not understood, don't panic. It was in 1960 the general theory of relativity came up. Following it, in 1930, some journalist approached Professor after Eddington, whom Dr. Rajbali referred, and asked him, "Sir, we have heard there are only 3 people in this world who understand general theory of relativity." Then, after Eddington just paused and said, "Who is the third one?" First is Einstein himself, second myself, who is the third one? So it was in 1930 that only 3 people in the world, probably 3 people in the world, understood general theory of relativity, and it is still as arithmetic as it was earlier. Okay, and then I hope most of you, or some of you at least, have read the book Brief History of Time by Stephen Hawking. Have you read that book? Has anybody read that book, Brief History of Time by Stephen Hawking? Okay, so Stephen Hawking in the early pages of that book describes how in 1930 the 4th person by then was saying to understand general theory of relativity in Cambridge, and that fellow was S. Chandrasekhar from India. That's a picture, nice picture from a group of scientists in 1911. Conference is known as Solvay Conference 1911, and now it's a series of conferences. Every third year it is organized in Solvay Institute in Brussels and Belgium. And you can see Einstein is standing over there in the back row. So he was quite young in 1900, though I mean he had a celebrated stature in 1911 itself, but he was standing there in back row. And here you can see other luminaries is Max Planck, Lorentz, and Madame Curie, and many others. And the same conference, Solvay Conference 1927. You can see 29 participants over here. All 29 were Nobel laureates. Either they were already Nobel laureates or they did receive the Nobel Prize afterwards. So here, the Einstein is in the central row. So here is Einstein. But from 1911 and 1927, within 16 years, he had reached that celebrated stature. And once again, you can see aging Madame Curie, Lorentz, Max Planck, and here is Niels Bohr, then Max Born, and Erwin Schrödinger, de Broglie. Most of these names you have heard of. So picking up a thread from Professor Rajbali's lecture, now I try to explain something about dark energy, which stems from the cosmological constant which Einstein introduced in his field equations, the lambda term which Einstein introduced and Professor Rajbali had shown in his presentation. So what is that cosmological constant? What is this dark energy? So statistics of the universe. Present size of the universe is 10 raised to power 23 meters. Why I don't present here, I'll emphasize it later. Age of the universe is something like 11 to 14 billion years. Somewhere you would come across as 10 raised to power 15 billion years or 13 billion years. The universe, as Professor Rajbali was talking about, is non-static, is dynamic, is expanding. It's continuously expanding. So there are two schools of thought. One is steady state universe, other is Big Bang school of thought. And according to the steady state universe, the universe was as it is seen today and will remain as we see it today. But currently there is some fallacy with that school of thought, because experiments suggest us that the universe is continuously expanding. In 1929, an astronomer called Professor Edwin Hubble convinced Einstein with his observations that the universe is expanding. And so the galaxies are moving away from each other. Now what does it mean? I will further elaborate. Not only galaxies, but the clusters, the local clusters, all of them are receding from each other. They are moving from each other. As they are moving away from each other, their speed of moving away is also increasing. And that is something referred as accelerated expansion of the universe, what Professor Rajbali was talking about. As the universe is expanding, its size is not constant. Its size is not fixed. So its size is ever increasing. If its size is ever increasing, the size referred here as 10 raised to power 23 meters is present size of the universe. And every moment the size of this hypothetical sphere, what we refer as universe, is increasing by a factor of 3 lakh kilometers. Okay. Then composition of the universe. The universe comprises of 74% dark energy, or the vacuum energy density, as Professor Rajbali was talking about. 25% is dark matter, 1% is baryonic matter, or the atomic form, of which all of us are made of, you, me, all inanimate objects. And don't panic if you find these figures bit fluctuating here and there. It's 73%, 23%.